guys, in this video we are going to learn comparator operations. These instructions perform a comparison of two values with the same data type. The first instruction is equal. It has the double equal sign. Then we have not equal. It means a number is greater or less than another number. The next instructions are greater or equal, less or equal, greater than, and less than. We can distinguish each instruction with its sign easily. Also, we have in-range instruction. It is used to check if a number is within a specified range. The out-range instruction is used to check if a number is outside a specified range. Then we will write a program using these instructions to control a simple traffic light. Let's get into it. First, let me add a counter. As you know, with each positive pulse, like this, the current value will be increased. Also, with the reset input, we can transfer 0 to the CV output. Now let's see the first comparator instruction, equality. For each comparator instruction, here we must determine the type of data which are going to be compared. Here I have selected the integer format. This line compares the CV value of my counter. Its name is counter1 with this number 10. So when the counter value is equal to 10, this output will be on. Also, on the right side, you can see its FPD program. The next instruction is inequality. For this one, when the counter value is equal to 10, the output will be off. Otherwise, the output will be on. Note that for the equality and inequality instructions, we can exchange their inputs. Their order is not important. Which input we use for the counter value or the number 10. Now let's see other comparator instructions. Greater or equal, less or equal, greater than, and less than. We can detect each comparator with its sign. For example, see the last line. Here, when the counter value is less than 10, the output will be on. If we exchange their inputs, the program logic will be changed too. You can use this rule to prevent any mistake. Place the first input on the left side of the comparator sign and place the second input on the right side to see their mathematical expressions. Well, here we have in-range and out-range instructions. In the first line, when the counter value is a number from 5 to 15, the output will be on. The out-range instruction works inversely. At the second line, the output will be on if the counter value is not a number from 5 to 15. Let's test some comparators. Here I have inserted an up count counter. On the right side, select the comparator operations list. I am going to insert an inequality instructions. First, I must determine which type of data is going to be compared. Let me select the double integer format for my counter and also the comparator. Here I refer to the current value of the counter and here I write 10. Now let me assign an output for this line. Also, let me use an outrange instruction. Here I select the double integer format. As you know, if I click here, I can replace the outrange instruction with its similar instruction, which is the inrange instruction. Well, let me complete this line and test the program. As usual, to change the input of my virtual PLC, I must use SIM or force table. But because of this block, I can right-click on every PLC address and change their values to 1 or 0. Let me do my modifications with Ctrl plus F2 and Ctrl plus F3 shortcuts. Now the counter value is 3, which is not equal to 10, so this output is on. Also, 3 is out of the range 5 to 15, so the second output is on. Now I can change the current value to see how these comparators work. Pause this video and try to test and learn comparator instructions. Now let's do a simple project. Here we have two streets A and B. I want to write a simple program to control two traffic lights. When I press A start push button, A street must be open for 20 seconds. During this time, the red light of the B street will be on. Then the yellow light will be on for A street. After that, the cars which are at A street must be stopped behind the red light and the B street will be open for 10 seconds. After that, the yellow light of the B street will be on for 5 seconds. Then this cycle will be continued until a stop push button is pressed. Let's start the programming steps. There are several ways to write an appropriate program. For example, we can write it with some pulse timers, but here I am going to use only one pulse timer. But I will need to use comparator instructions. First, let me insert a start contact. Now I need a pulse timer. One cycle of the traffic light lasts 40 seconds, so the preset time of the pulse timer is 40 seconds. Also, this cycle works frequently, and I know after 40 seconds the Q output of the pulse timer will generate a negative pulse. So I can use this pulse to start the timer again. Now let me use a reset timer instruction and a contact to stop the timer every time I want. Well, let's test this part of the program. As you can see, when I activate the start contact, the timer starts its work, and after 40 seconds, it restarts. Also, every time I can reset the timer time to 0 with the stop contact. Now let's complete the program. To turn on the green light of the traffic light on A street, which I call green A, I need to detect the time when the current value of the timer is greater than 0 and less than 20 seconds. Let's exit from the simulation. Okay, I need two comparator instructions. First, let me insert a greater than comparator. Well, first let's change the data type to time. At the top of the comparator, I refer to the elapsed time of the pulse timer. At the bottom, I write 0. Pay attention, when I stop the timer, its elapsed time resets to 0. At this moment, I don't want to turn on any light. So here I have not used the greater or equal operand. Also, the timer's time must be less than or equal to 20 seconds, so I need to use this comparator operand. Finally, as you know, this condition will turn the green light on. Pay attention here. There are two ways to write a program, based on the conditions or based on the outputs. Let me explain the first way. Well, the first condition turns on the green A light. Also, it turns on the red B. So I can make a branch in my program to turn the red B light on. But this way is not true in PLC programming. Why? See the next condition. This condition turns the yellow A and red B lights on. Now suppose the timer is at 10 seconds. Based on the first condition, the red B light must be on, but the CPU turns it off because of the second condition. The second condition takes priority over the first one. I must write my program based on the outputs. I have to use one output for each light in the program and then find which conditions turn them on. Let me come back to the TIA. Let me define tags for my PLC inputs and outputs. Well, in this network, I am going to write about all conditions which turn on the red B. The first condition is like the previous network. Okay, the second condition is when the timer is greater than 20 and less than 25 seconds. Alright, this is my program based on the outputs. I expect you to test this program with the TIA and the watch table. Now let me test it on my PLC. As you can see, always to control two traffic lights, two outputs of my PLC outputs are on. Now we are going to learn how we can define and use the math functions. First, we will have a brief review of data types. Then I will explain the math functions that I can use in the TIA. And finally, I will do a simple project. Alright, let's see some basics of the data types. See this table. The first data type is Boolean, which includes 1 bit. 1 bit has 2 states. It can be used to represent if a digital input-output is true or false, or on or off. Also, a bit of the PLC memory is 1 or 0. Remember, the first number refers to the byte number, and after the point, the second number determines its bit number, which can be 0 to 7. The next data type is a byte. It includes 8 bits. We just write byte number to refer to a byte, such as MB0. With 8 bits, we can store 8 zeros to 8 ones using a byte address. These 8 bits can be used to represent a number from 0 to 255. Let me calculate power 8 of number 2. It is 256. This number shows the number of all states that 8 bits can have. So with 8 bits, we can represent the numbers from 0 to 255. Pay attention. There are 4 standards to represent a number: binary, octal, decimal, and hexadecimal. Usually, we use decimal numbers in our daily lives. But in computers knowledge, other standards are used frequently. For example, now you can see the 4 represents the number 3. Now I have the 4 representing the number 255. It was a short review of these standards, which probably you studied at school. Let me continue to see other data types. A word is 2 bytes or 16 bits. Here we use the W letter between M and the byte number. MW0 includes byte 0 and byte 1. It can store numbers from 0 to 65,535. A double word is 4 bytes or 32 bits. With a double word, we can store bigger numbers. Now pay attention to the unsigned integer and integer formats. Like the word format, these need 16 bits, but they use different rules to store numbers. The unsigned integer format uses all 16 bits to store positive numbers from 0 to 65,535, but the integer format uses its last bit for the sign, 0 for positive and 1 for negative numbers. It just uses 15 bits to store numbers. For the last bit, 0 means a number is positive and 1 means the number is negative 1. So the integer format supports numbers from -32768 to 32767. The double integer format with 32 bits supports a larger range than a simple integer number with 16 bits. For fractional number, the real format is used. It uses 32 bits like the double integer format, but its storing way is different. Let me open the help window of the TIA. Here search data type. Click here. On the right side, you can see different data types. Click on floating point numbers, which use the real format. Click here. Now you can see how the real format uses 32 bits to store fractional numbers. Well, the math functions work based on numbers. It was necessary to review basic data types, which are used in the TIA. Now let's start learning the math functions. These instructions are here. Well, let's start with addition. This is the ladder symbol of the add function. For math functions, we need to determine the data types of their inputs. This function is used to add a value at input IN1 with the 1 at input IN2 and query the sum at its output. Here we have two values from two counters, 10 and 6. The summation of these numbers is 16, but here is 0. Why? The add function and also the other math functions have an enable input. Here, if the I0.0 input is activated, then the add function will do its work and it stores 16 in the MW1. The subtract instruction subtracts the value at input IN2 from the value at input IN1 and sends the difference to its output. Note that if I click here, another input will be inserted into the add function. So I can use the add function to add 3, 4 or more values, but the subtract function doesn't have this feature. Now let's see other functions in the TIA. This is the ladder symbol of the multiply instruction. Here, this function multiplies 10 with 6 and stores 60 in MW1. As you can see, this instruction can multiply more than 2 values. The next instruction is division. Here, this instruction divides 10 by 6 and returns its quotient. The next instruction is MOD. This instruction divides the value at the input IN1 by the value at input IN2 and sends the remainder of the division to its output. See this division to learn the last two functions. Alright, we can use the increment instruction to change the value of the in-out parameter to the next higher value. Pay attention. Here, both input and output addresses are MW4. The value of this address will be incremented by this positive signal edge. Suppose I press the I0.0 push button for a half second. As you know, the scan cycle time is about 0.5 milliseconds. So when I press the push button once, the PLC executes this line thousands of times. If I want to change MW4 from 13 to 14, I must use a positive edge instruction. Note that if I use a normally open contact, the MW4 value will be increased rapidly. Well, the next instruction, decrement, works inversely. For example, it can change the stored number in MW4 from 12 to 11. The next instructions are used to find the minimum or maximum values. For example, the minimum of 10 and 6 is 6. Note that these instructions can have more than 2 inputs. Here the max function chooses 10 from its inputs. Well, the negative function changes the sign value at the IN input. For example, if it is 12, this function will give us minus 12. Or if the input value is minus 5, it will send 5 to its output. ABS is the used syntax of the absolute function in many programming languages. This instruction gets the absolute value. For example, for the minus 12 or 12 values at IN input, we will have 12. Alright, the next instruction is used to limit the value at IN input to the values at MN and MX inputs. If the value at the IN input is between MN and MX value, it will be copied to the output. For example, here if the counter value was 2, 3, 4 or 5, it is copied to the output. But now it is 10, which is greater than the MX value. So instead of 10, we will have 5 at the output. If I reset my counter value to 0, which is less than 2, the output of the limit function will be 2. The next instruction is used to create a function. Let's see that in the TIA. Alright, here are the math functions that I explained their applications. Let's insert the calculate function. To choose the double integer format, click here. Here you can see an example to define a function, and here you can see the operands that you can use. Let me define a simple function. Note that I can click here to add another input. Let's insert two numbers. First, I write 4. Here is a simple and important point. If I write a 7.0 instead of 7, the TIA stores that using the real format. What is this rectangular? Pay attention. My function works based on double integer format, but its second input has real format. This rectangular meaning the TIA tries to convert the number in the real format to a number in double integer format. Sometimes this converting causes the TIA to get a wrong result. Let's test this program. Alright, the exact answer is minus 3.66. The double integer format omits its fraction part and shows it as minus 3. Let me change the formats of the inputs to real and test the function again. As you can see, at this time, my program calculates the answer properly. Alright, the math functions which I explained already are simple. The main point is to take care of the format of the data. We learned some basic data types and math functions. Now, we will complete the math functions and do a simple project. Also, we will learn how to use the cross-reference table and define functions during the project. Alright, here you can see the other math functions. The first instruction is used to square the value of a floating point number at its input and to write the result on its output. The next function is used to form the square root from the value at its input. This instruction has a positive result if the input value is greater than 0. If the input value is less than 0, the output returns an invalid floating point number. The next instruction calculates the natural logarithm to the base number E, which is 2.718282. Well, this instruction calculates the exponent from the base number E and the value specified at its input. Okay, this instruction determines the decimal places of the value at its input. For example, for 23.5, it just returns 0.5. Well, we can use the exponentiate instruction to raise the value at the first input to a power specified with the value at the second input. Here the instruction raises the value 2 at the first input to power 3, which is at the second input. Its result is 8. Okay, now you can see trigonometric functions which can be used in the TIA software. For example, see the first instruction, cosine value. This instruction calculates the cosine of an angle. Pay attention to the size of the angle specified in radians at its input. The next instruction is arc cosine, which is used to calculate the size of an angle from the cosine value, which corresponds to this value. Only valid floating point numbers within the range -1 to 1 can be used at the input. The calculated angle size is in radians. Its range is from 0 to the pi number. This number is about 3.14. The next functions are the sine and tangent values, and respectively their inverse functions. When you are using math functions, pay attention to their domain and range. Now let's do a simple project. Try to write a program to calculate this function, where x is 1500 and y is 500. Pause this video. You can do it in many ways. Then compare your program result with mine to check whether it is correct or not. Then write a function to calculate this function for any x and y values. Now I am going to write a program to calculate the math function. First, I insert the add and the subtract instructions from the right list. I select the real format because my numbers can either be an integer or a fractional. The real format supports both of them. This format needs 4 bytes to store a number. Pay attention, I have used the MD0 address, so the next free address of the memory is MD4. Now let me define suitable tags for the entered memory addresses. Now let me insert SQRT and exponentiate instructions. Now let me complete the second line of my program, like the previous one. Here, the exponentiate function uses the number 2 as its power instead of 3. Now I need to sum up the results which we got in the second line. Let's test this program. This is the result. I have calculated my function with the Windows calculator. As you see, the PLC result is wrong. Why? As I mentioned earlier, math functions are simple, but we need to care about the data type and the entered addresses. We must use separate memories to store each number. Now I am going to use the cross-reference table. Let me select my PLC and then click on the cross-reference icon. This table shows all used objectives in my program. From this list, let me select this filter. Now I can see the used OB1 block and all of the used tags. For example, if I click on this tag, this table shows it used this tag twice in the first network. The program just read its value one time, and at another instruction it writes a number on this address. Click here to check overlapping. As you can see, 3 tags have overlapping with at least one other address. For example, select the first address and click here. At the bottom, this table tells me that the selected address has overlapping with 2 addresses. To have an image of the used addresses and what is overlapping, click here on the program info. Here is some information about the program. Click here. Here, there are 2 tables which show input, outputs, and memory assignments. We have used memory addresses in the program, so see the right table. Here, pay attention to the D word column. Remember, we used MD0 to store X plus Y. This address includes byte 0 to byte 3. And then we have used the next free memory address MD4 to store X minus Y. This address uses byte 4 to byte 7. This table tells us that we have used 3 D-word addresses which have overlapping together. This is my programming mistake. For example, the byte number 10 is used to store 3 numbers at the same time. The square root of x plus y, power 2 of x minus y, and the final result. As you can see, after the MD8, the next free address is MD12. So let me modify the address of this tag, power 2 of x minus y, in the main block. Let me right click on the desired tags and select Rewire tag. Here, let me change the address to MD12. As you can see, the overlapping problem has been resolved for the power 2 of X minus Y tag. For the final result tag, the next free address is MD16. Pay attention, it is not necessary to use exactly the next free address. I can use MD17, MD18 or MD19 because these addresses have not been used yet. Let me change the address of the final result to MD17. Now the overlapping problem has been resolved. Now let me define two extra addresses, an input address and also a bit of memory. Now you can see the two used addresses in this table as well. Let me come back to the program and clear these extra addresses. Now let me test the program again. At this time, the program calculates its final result correctly. Let me exit from the simulation mode. Alright, here is a better way to do this project. You have learned how to use a function before. Here we can define inputs, outputs, or local variables for a function. I want to create a function that gets x and y in real format and returns a real number as its output. Now I am defining x and y variables as the function inputs and the final result as its output. I select the real format for these variables. Also, I can define some internal variables to use only in this function. I can write the previous program here. I just need to use x and y instead of constant numbers. Also, let me use internal variables instead of memory addresses. And don't forget to use the function output variable to return the final result. Now let me use this function in the main program. As you can see, this function has two inputs and one output. It can get two real numbers and return the desired value. You can use this function many times, so if a part of the program needs to be repeated, you can write it once in a function and use the function many times. Now let me test this program. As you can see, the function result is the same as the previous program. Thank you for watching.